how much of it? Where did we last stop off? Can any of you like just go through your notes, quickly check and tell me?
So last class we started discussing about colloids. After we started discussing about colloids, we differentiated in types of colloids and the different. Ma'am, just a second.
So we had different types of colloids, lyophilic, lyophobic, for macro, multi-molecular.
Yes, from macro, multi, yeah, exactly. We discussed that as well. Then I think, wait, where did we stop? Just a second.
Dhriti, Ansh, what did we do after that?
Then we looked at micelles more in like detail.
How are they formed? How?
Yeah, how are they formed? Then the critical micelle concentration CMC thingy that we looked at that.
That is
Then
for formation of missiles.
yeah, then
ultrafiltration and all that also we did.
Yeah, what did that?
I think now we have to start with like not those properties but those effects.
So, I want you guys to get warmed up. So we discussed ultrafiltration, all of that, right? What does that come under? What is ultrafiltration for?
Purification of colloids.
Purification. Like if you had to separate the components. Yeah,
so there were three, I think dialysis, electrodialysis, and ultrafiltration.
Purification के पहले preparation का भी discuss किया. You remember what the methods of preparation are?
Yes,
decomposition.
Yeah, oxidation, hydrolysis, reduction.
Hydrolysis and reduction.
Yes.
Crystallization. Arc method. Okay, so that you get.
Can you repeat that?
Okay, preparation methods you guys need to revise. Purification, yeah, at least you have an idea of what comes in that. Then we were discussing properties of colloids. So we had discussed 4 of those properties. Some of them are like very, very similar to what you already studied, similar to what like solutions K properties. So colloids also show you have, what do you call it? Colligative properties, like based on the number of particles, vapor pressure, boiling point, melting point, freezing point, all of that. Then color, again, colloidal particles, suspended wavelength of light interacts with it, ends up coloring the solution, sorry, the colloid. Then okay, sorry.
Yes, it's your WhatsApp which is ringing, right?
From my end, yes.
Yeah, sorry.
Okay. Tingle effect, again, light is scattered because the particles are big enough to do that. In true solution, light just passes through without any change. Suspensions it is basically like just cut off, like they're opaque. Colloids, they are just enough size to scatter light. And then colloids again, the particles are suspended, dispersed within that medium, right? So they show Brownian movement. Then we come to another, like the next few properties we'll be talking about are quite important because they touch on stability of the colloids and like proper properties of the colloids itself. The 5th one, charge on colloids. Okay, so colloidal particles have charged, they are always charged. They're always charged. Okay, for example, like obviously like particles ke upar there's a specific charge, but overall it's all neutral, just like with solutions and other things. Just that, like for example, if you recall soap solution, soap के केस में, do you remember what is a soap molecule? If you put soap in water, what do you get?
Salts of potassium and sodium.
Soaps are salts of, like, no, sodium or potassium salts of what acids? Like, kiske salts hai?
Fatty acids.
Of fatty acids, right? Correct. So carboxylic acids are essentially there, or sulfonic acids. So you have hydrophobic, and then yahan pe, where at this point where either potassium or sodium ion is like bonded, where it is ionic bond, salt jahan pe form hota hai, to is pe what charge would you expect to be here on the head, the hydrophilic end?
Positive.
What charge? Positive. Kyun?
Negative, no, because K plus and Na plus are already plus.
So they are attracted to the negative charge. See, Ansh, fatty acids hai na, carboxylic acid, like for example, if you take acetic acid, it is CH3COO minus. So similarly, soap ke case mein you have same thing, but on the scale of C18H35, then COO minus, like that. Okay, so yahan pe you have negative charge. So when soap micelles are formed, because this is water, the hydrophobic is repelled away from water. They're all like aggregating inside, and the hydrophilic ionic end is what is there outside. So if I look at each soap micelle, उसके ऊपर किस तरह का charge रहेगा? Like if I take a ball of soap micelle, this is kind of how a soap micelle looks like, right? तो यहाँ पे fatty acid, यहाँ पे negative charge है. तो a soap micelle, it will be like, what sort of a charge will I find on it? Positive or negative?
On the entire missile.
Huh.
Neutral, because it's both positive and negative.
Soap is neutral. Like if I take a random soap molecule, isolate it, it's neutral. But पानी में डाल के, this is dissociating. तो यहाँ पे एक ionic end है, यहाँ पे hydrophobic end है. So this is what is happening. Like all the hydrophobic accumulates together, so this associated micelle is being formed here. So this micelle, look at the structure of the micelle. So hydrophobic is all inside, and the ionic end will be pointing outside. So based on this,
so the ionic point which is ending outside will be negative, wherein the Na or K plus molecules will get attracted, right?
So each micelle, because on the outside you have this ionic end of the soap molecule being formed, so each soap micelle will be negatively charged. And the K plus Na plus are just like chilling in the solution, just surrounded by it. Okay, so this is just an example. So that way, any colloid that you take, like even milk, will have charged particles. Like the dispersed phase are always charged. So colloidal particles are always charged. If you have a doubt ki like everything should be neutral, charge kahan se aa raha hai, it's like this. The sol, like the colloidal solution, net charge is 0, but on the dispersed particles, on the colloidal particles alone, there is always some charge present. And in fact, the charge is what is contributing to the stability of the colloid. So that we'll go deeper in this section only after some time. So colloidal particles are always charged, and the charge that is there on the colloidal particles So the charge is same on all colloidal particles. Okay, so अगर soap solution form हो रहा है तो all the soap missiles will have negative charge only on them. अगर दूसरा कोई colloid ले रहे हैं, like for example positive colloid, blood में hemoglobin का colloid if you're taking, all the hemoglobin particles will always have a positive charge because of that Fe that is there. All the metal salt like hydrated metal oxides will have positive charge only. All the metal colloids like gold in a solution, copper, K-sol, all of that will have negative charge only. That way it can be
Can
either.
you repeat which have positive and which have negative?
I'll give a list of examples, positive ke liye, negative.
Okay, ma'am.
But the point is, it is either positive or negative. But if I take a particular colloid, it will always have the same charge on all the particles, always. Okay. So coming to examples, positively charged colloids. Positively charged colloids, you have hydrated metal oxides. Hydrated metal oxides, you can think of it as rust. Another example is like textbook mein jo examples are given, aluminium oxide ka, like Al2O3 is the metal oxide, XH2O. So you have water molecules surrounding or within the lattice structure of this. So if you prepare a sol of this, so they are positively charged. Another example is copper oxide, chromium oxide, copper. So CrO3, XH2O. Then the basic dyes, like basic dyes matlab dyes that are basic in nature. So methylene blue, for example. Hemoglobin is an example of a positive charge. Hemoglobin mein iron hota hai, that's what helps in like the oxygen bonding to it. So the iron like contributes to the positive charge. Oxides, if you prepare any oxide, any metal oxides ke sol, they are also, you'll observe positive charge on them. For example, titanium dioxide sol. Similarly, examples of negative sols. So metal salts, like pure metal salts. Copper, Ag, Au. So you prepare these in solutions like in water.
Just one question. Positive mein oxide example is TiO2 solution, right?
Sol. Solution, you use it for true solutions. Colloids may you usually come across sol. Remember, if you mix solid and liquid, it's called a sol. Okay. Metallic sulfides also come under negative sols. Common ones, you prepare As2S3 arsenic sulfide, antimony sulfide, cadmium sulfide, CD is cadmium. So then acidic dyes. So basic dyes are positively charged, acidic dyes are negatively charged. So examples of acidic dyes are eosin, Congo Red, and we have one more. Like biomolecules ke, like carbon based salts like starch. Starch is basically your carbohydrate suspended in water, so that's a negatively charged salt. Gelatin, like what you prepare gels and jellies with, agar agar ke saath ya gelatin ke saath. clay, charcoal.
Miss, can you repeat the examples of acidic dyes?
So this is one eosin. Is it visible or is it going below the screen?
No, it is visible.
It's
The
visible,
spelling
ma'am.
is weird.
Eosin, Eosin. The other one is Congo Red. Actually, show pictures better.
And miss, this starch, gum, and all that also comes in acidic dyes only.
Everything in black I've written acidic dyes.
Miss, you have written all of negative in black.
Oh, did I say positive? No, yeah, all of negative is in black. All of the positive ones are in red.
No. What I meant is acidic dyes में ये starch, gum, gelatin,
Oh,
clay, charcoal.
sorry. This is the fourth one.
Okay.
Like,
got
or like, look at this. Or like, these are not dyes. They are all like,
yeah, they're not acidic dyes. They're just another part like metals, metallic sulfides, acidic
Yeah.
dyes, and stuff.
they're a class of compounds. So these are all carbon-based macromolecules. Like starch, gum is what you get from rubber tree, like resin kind of substance. Gelatin is, again, you get it from, it's organic, it's big, like
We use gelatin to make jelly and that stuff, right?
yeah. Clay, charcoal is, again, you get it from wood. All these are biological macromolecules. Yeah. Okay. Ansh, Mitali, Shantanu, if you guys are done noting down, I'll show you guys some of these dyes. If you had bio labs, you would have used these dyes. Like you use it to stain your cells so that you can like observe it.
Like a laboratory practice, which we in school.
Yeah. If you had to observe.
Yeah, we may have. Now we may have. They are going to be taking practicals also.
I remember in my school, like bio, like to observe onion cells, we had to add like 2 drops of methylene blue to get that thing. Yeah. Yeah. So this is what methylene blue looks like. It's like a bright, brilliant blue. No wonder it's used as a dye. Needs to color things. This is the structure of methylene blue. So you can see that there is a positive charge here, which means that it'll be surrounded by a negatively charged thing. So that ends up being the negative sol. So how the sols exist, I'll we'll touch on that later. But yeah. So you have oppositely charged thing.
The color is nice.
It's a brilliant blue. This is Congo Red. Again, like a really deep red. You can see this is also another complicated organic molecule. Yeah. This is eosin. So, you have eosin, you have nigrosin. Aqueous solutions of those, but essentially coloring agents. It's got a reddish pinkish kind of a thing. This is a darker blue. Yeah. The most common use of dyes, like if they react with like in a particular way with acidic or basic substances, you can use them as indicators, or majority of the times you use it to stain, cells, to stain bacteria, things like that. Yeah. Should we go to the next part? Ansh, Shantanu?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So I mentioned charge is quite important because charge is responsible for the stability. How is it responsible for the stability of a colloid, of a solvent? So what happens is, like, let's say you have, this is your container.
Miss, this you have written it as a statement and now you'll be giving reasons for it, right?
It's kind of an explanation, not, yeah, reason or explanation of how is it responsible for stability.
Yeah, so it's like they've given a statement and give reason sort of thing, no?
Huh. Yeah. It's not going to be multiple points. It's going to be like 1 point only. So imagine you've got a sol here. Then you have charged particles. Now all colloidal particles have the same charge. So, we just saw like unme Brownian motion hota hai. So if two of these particles get close to each other, what will happen? When two like charges come near each other, what will happen?
They'll repel.
They'll repel. They'll push against each other. So that is why that you won't have any aggregation or coagulation of all the colloidal particles. So they won't like come together and sit down like a suspension. Because there's constant repulsion, they're always pushed against each other and they end up, just being spread out throughout the thing, which is what a colloid is. That's what makes a colloid. So basically, they're responsible for the stability of the colloid. So the reason is that you have no aggregation or coagulation. Why? So this is the reason, due to repulsion between the dispersed phase particles. Okay. So charge on colloids, all colloid particles are charged, and all the colloid particles have the same charge because they're made of the same thing. They behave the same way. So if they have the same charge, they're not allowed to come close to each other because the repulsive forces act up. So you won't have any aggregation or coagulation. So that results in them being spread out, dispersed throughout the medium. So which is what a colloid is. Okay. So then now we'll look at why are these particles charged? Like where is this charge coming from?
Miss, what does DP stands for?
Dispersed phase. The dispersed phase particles, colloid particles. Okay, Liklo, let me know when you guys are done. Then we'll discuss origin of charge. Okay. Okay, Ansh and Shantanu, are you guys done? So this needs a little focus. That's why I'm just waiting for you to be done. Okay.
Yes, ma'am.
Okay. So charge is due to so there are multiple reasons where that colloidal particle can get charged. It depends on what colloid we're talking about. Sometimes it may be due to friction between the colloidal particles itself. One may take electron, the other will give electron. Between the dispersed phase particle, between the dispersed medium particle, वैसे random van der Waals, because of random collisions हो सकता है. main reasons why we observe is two of them. One is electron capture by Sol particles during electrodispersion of metals. Okay, so in order to understand this, electrodispersion of metals. So do you guys remember the preparation of metal salts by Briggs arc method? Like, we've seen a video also of it. Do you remember what happens? Excuse me. Excuse me. Just yes or no, guys. If you remember it, I can pick it up. If you don't, then we'll revisit that.
Yeah, can you show the video again?
Ma'am, can you revisit it?
Okay. Oh, I'll watch the same video that we saw before.
I can teach you music 150 times. In making the colloidal solution, firstly I can take the glass that is full of water, and then I pour the glass in the beaker, which is
Okay, never mind. So you can see, like, this is Briggs arc method. You have a container ice bath, and then you create that electrolyte, and then you produce a arc between electrodes, and that basically vaporizes the metal, and then that causes like dispersion of metal throughout this thing. And we're putting it in an ice bath because you want to condense that metal vapor back into solid phase so that it's dispersed throughout. Now, do you remember? Like, making sense?
Yes, ma'am.
So the arc vaporizes metal, and then the metal vapors condense because
Hence, and they form a sol.
and then that ends up being forming a sol. So during this method, if because you're using electrical arc, electrical energy and all that, if any of like the sol particles end up picking up some of the electrons and they end up having a charge. So that is what is theorized.
So
that-
again, that charge leads to the suspension, so they won't aggregate, and then
Yeah,
it's
at
the
the
same
end of
thing.
the day, like ye jo bhi hai, this whole thing, charge kahan se? Yeah.
Okay, ma'am.
So if if there's electrodispersion going on, they may capture a random electron by the Sol particles during this thing. Another thing, like another theory is that this is this thing. So this is the preferential adsorption. So preferential adsorption of ions from the solution. So this requires a little more elaboration. So I'll just put it here and then I'll get into the explanation. So during the formulation of the or let's like during and the formulation. Electrical double layer. Okay. So here the main keywords that you guys need to note is it's a preferential adsorption of ions. Solution matlab, like basically we're talking about the dispersed medium. And there's a electrical double layer that is being formed. So these are like the main keywords, key points that you just taken. So we'll elaborate. I'll elaborate this using an example. Okay. I'll need slightly more space than this, so I'll go to the next page. So like finish writing it. So once you're done writing, like do not write, pay attention here because it needs some focus. So between all of the theories that are proposed, this is the most accepted one. Okay. Shantanu, Ansh, and Dhriti, once you're done. we'll go.
Yeah, ma'am, done. Just finished.
Okay.
Yes, ma'am.
Okay. Ansh, you also?
Yes, ma'am.
Okay. So we'll take an example. So silver nitrate, AgNO3, if we mix this with potassium iodide, obviously both of them are in aqueous solution. Can you predict the products of this reaction? This is an.
Ma'am, can you repeat that?
Can you complete this reaction? Silver nitrate plus potassium iodide.
Ma'am, wouldn't a displacement reaction take place in like potassium nitrate and silver iodide? So
Absolutely.
K2NO3
K2,
and K2NO3.
KNO3. NO3 is
KNO3. Ah, it's not 2 minus. Sorry. And AgI.
correct. Usme se AgI is a precipitate. This is insoluble. So this forms
Yes,
as a
ma'am.
precipitate. Potassium nitrate is a soluble salt. So potassium and nitrate ions remain as it is in the solution. They are always dissociated. Okay. This is like a chemical method to prepare AgI sol using this. Okay, so you have AgI. It's insoluble, so it ends up being a colloid. You can prepare a colloid out of it. So what happens is, now you just, in order to prepare AgI, you need this plus this. It doesn't matter what you add to what, but depending on whether you take Ki solution or AgNO3 solution as the base, you end up getting either a positive colloid or a negative colloid. Okay, so here's what happens. Okay, suppose if AgNO3 is added to Ki. Okay, AgNO3 added to Ki matlab, imagine you're mixing both of these. Prepare करने के लिए you'll take a solution like a beaker or a test tube or whatever, where you want to get your final product, right? So suppose that final, like that particular test tube already has Ki in it, potassium iodide. So isme already you have K plus and I minus floating around. So within this, if you're adding AgNO3, so that's the situation. So already Ki hai, K plus I minus dissociate hoke, it is there in the solution. Into this, you're adding AgNO3. Then your product AgI is only formed, but the AgI that is formed absorbs the I minus ions. Okay. So in this previous point, when I said preferential adsorption, there was one more point that I missed out on. So this particular preference, is basically to the ion. Usually the ion that is common to both dispersed phase and the dispersed medium.
Ma'am, could you elaborate a little bit more on the example and put it in words of this statement?
Yes, I will do that. Just a minute. So like what has been observed is, like, look, this is the theory, right? We said preferential adsorption of ions from the solution, like dispersed medium jo hai, like already existing solution jo hai, or uski wajah se, because of that adsorption, there's an electrical double layer that ends up being formed. So taking our case, so this preferential adsorption, when we talk about preferential adsorption, this adsorption, like the preference is for the ion that is common to the colloidal particles. So applying it to this case, we have AgNO3 plus Ki giving AgI precipitate and these things. This is the basic reaction that happens. Now in the first case, I told if silver nitrate is added to Ki, matlab you have a Ki solution existing. So you're preparing this colloid in Ki solution. Okay, so AgI is the precipitate. So AgI forms the dispersed phase, which is like dispersed throughout the solution. Now, with among the ions present in the dispersed medium, like solution mein jo ions hai, you have K plus and I minus. Which is common with AgI, existing AgI? Iodide ions, I minus ions. So what happens is, in the test tube, like suppose you have some AgI molecules here. Molecules are like a clump of AgI molecules because it forms a lattice and it is not dissociating, it is insoluble. So this AgI will adsorb, matlab iske surface pe there'll be a bunch of I minus ions coagulating or like adsorb, like just accumulating. So is AgI ke surrounding, you have some I minus. Around this AgI, you have some I minus. Around this AgI, you have some I minus. So because I minus are surrounding all the AgI particles, and that's causing the whole AgI to be precipitated in this test tube, you end up getting a negative salt.
Ma'am, but I still have a doubt about one thing. That is that now that you've taken like a Ki solution, so K plus and I minus is my dispersion medium. It's the solution,
Yes.
correct? Then
Yeah.
you add AgNO3, that also disperses into Ag plus NO3 minus, and then Ag and I react to form the precipitate because it's an insoluble solution.
Correct.
So wouldn't all the iodide ions get used up when the precipitate is formed?
So that's where this particular nuance is important. So you're adding AgNO3 into Ki. So if you take it stoichiometrically equal, then yes, you will find AgI niche. And if you take excess of silver nitrate, then okay, like it'll precipitate off. But if you have I minus in excess because Ki के solution में prepare कर रहे हो, then all the extra I minus that is already present in this will form this particular colloid.
Okay, so there is like a difference in quantity taken because Ki is the solution and AgNO3 is in a much relative lower amount
Yes,
than the solution.
relatively lower amount.
Okay.
Yes.
So
See,
ma'am, what happens to the okay.
so
No.
on the flip side,
Yes, ma'am. Got
if
it.
you invert it, if I take AgNO3 nexus, if I add Ki, so Ki is added to AgNO3. So इसका reverse ले रहे हैं. So in this case, I'm taking a test tube जिसमें silver nitrate solution है. मतलब I have Ag plus and NO3 minus floating around here. And इसमें I am adding Ki. Then what happens? So Ki will dissociate into K plus I minus. ये reaction होगा and AgI will be formed.
Ma'am, it will be the opposite of the first reaction, right? So we'll have preferential adsorption of NO3, I think.
No. So the preference is for the ion that is common to the colloidal particles.
Oh, so it will still form AgI.
AgI will
But-
be formed, but AgI ka preference is for, it will be for either silver ions or iodine ions because that's what it
Okay.
contains, what it is. Like,
So it's in a silver nitrate solution. So silver ions will become preferential, right? Because the number of silver ions are more.
Correct.
Okay.
so
Now I
ये
got it.
silver ions के का solution है, so you'll have a bunch of silver ions floating around. So the silver iodide precipitate will absorb Ag plus. Okay. So basically, depending on kiska solution ले रहे हो, that particular ion will be in excess, so it's going to absorb that. So the preference क्या absorb करेगा? The preference is for whatever is there in common with this. So AgI will always absorb either silver ions or iodine ions. तो दोनों में से what is available will depend on originally क्या solution लिया इसमें. So if I took Ki, I minus is the common one. If I took AgNO3, Ag plus is the common one. So it's gonna absorb those ions based on that. Okay. So you have to see what is already present before you're adding your other thing. Ki is already present, matlab that will be there that way. So I'll give you another example. So one, this will be two. If I add FeCl3 to hot water, then I get metal oxide, hydrated metal oxide. So Fe2O3 XH2O. This is going to absorb Fe3 plus. And if I add FeCl3 to NaOH, like basic solution. So basically I have Na plus and OH minus in this. Then we observe that this particular colloidal solution absorbs OH minus ions because it's a basic thing. OH minus, like it'll be common to both. So you end up adsorbing this thing.
Ma'am, I didn't get it.
So like this is what, so if we add iron chloride, FeCl3, ferric chloride, to hot water, excess of hot water is neutral, then like obviously this does not have like other compounds or something. So what is observed is it ends up adsorbing iron 3 plus, ends up forming a positively charged sol, and when you add FeCl3 to NaOH, so alkaline solution, matlab OH minus is in excess, then we observe that this adsorbs OH minus preferentially, and it ends up forming a negative sol, negatively charged sol. Just two examples that we have taken. In this case, we precipitated it using the double decomposition reaction, double displacement reaction. When it is available, it's going to adsorb what is common to both the things. In this case, you're just adding it to either neutral hot water or to NaOH, like a basic solution. In that case, then this is what is the observation that we see. So Fe2O3, hot water matlab you would have H plus OH minus, like it's going to adsorb ions rather than the other ones. And if we add it to NaOH, because there's some extra OH minus ions, it's going to adsorb the OH minus ions preferentially, because it's a hydrated oxide.
Yes, ma'am, got it.
Yeah. Now let's come to the next part of the statement. Preferential adsorption, ठीक है, वैसे हो रहा है, and it's picking the ions from the solution, like surrounding it, जो भी solution है. Now, what is this electrical double layer that we speak of? क्या हो रहा है? So, ऐसे adsorption हो रहा है. So, I'll continue with the silver nitrate Ki example only, because you have a lot of things to play around with. So, you have AgI ka clump particle, whatever. This is the precipitate that's formed. It's attracted I minus ions, let's say. We're taking the first case where you added silver nitrate to Ki. So adsorption is basically accumulation of all these things around it. So it looks like this, right? Now, this negatively charged sol particle is going to attract.
Miss, one second, can you go to the previous page?
Okay. Are you noting this down, Kya?
No, I just had to see something there.
So I'm taking this case, like Ki is in the solution. So you have
Yes, ma'am.
K
Got
plus
it.
I minus just roaming around. And then when you add silver nitrate, AgI is precipitating. So because iodide is common to both, it adsorbs I minus. So that's what we've seen till now. AgI precipitate form hua, so it immediately adsorbs all the I minus particles around it. So I got a negative sol here. So now, because this is negatively charged, abhi solution mein kya hai? So we have AgI particles. In the solution itself, I have K plus and I minus also. I minus is already like surrounding the AgI particles. So I have K plus, right? So if this colloid particle has negative charge, it will attract positive charge because opposite charges attract. So around this layer, so this is like a charged colloidal particle, this will again be surrounded by K plus.
So, ma'am, that's why the definitions or the statement says that there are it becomes like a double layered colloid.
Correct.
Okay.
So you have So what is it exactly? Electrical double layer. So you see there's like two electrical, like two electric charges. So this is layer 1 and this is layer 2. Okay. So that's why we say, so within this, the first layer, sorry, let's call it, so first layer, inner layer, basically, the first one that's actually wanted, like absorbed by AI. So in this case, I minus. So this is called the fixed layer because that's like a property of this solve. And the second layer, because it's like a secondary thing, it's occurring only because this already has like the first round of charge. So in this example, what is K plus? So the second layer is called diffused layer. So this is the fixed layer. This is the diffused layer. So if I had to color code it, so the layer in blue where I minus is there, so that's the fixed layer. And the outer layer, K plus ka layer jo hai, so that's the diffused layer. Just the terminology that we use. And this kind of a phenomenon, so this has like a proper, like this double layer is called, like this whole thing. So that's called Hemhodes electrical double layer. Again, these are just words, terminology, just so you know in case you come across it. So if you come across Helmholtz electrical double layer, we're talking about colloids where this sort of a thing is formed. You have colloids are charged particles, they attract oppositely charged particles from the dispersed medium. So you have an electrical double layer, like two layers of charged particles. That's why electrical double layer. Helmholtz is a person's who worked on this. Uska naam hai. So in this example, I took I minus K plus. ये reverse भी हो सकता है. Like if you're talking about the other sol, if it's a positively charged sol, then ऐसा भी हो सकता है. You have AgI surrounded by silver का positive ions. This forms a positive sol. And this in turn can be surrounded by negative NO3 minus, जो भी है solution में. Cl minus, like जो भी है. So whatever case you take, whatever situation you take, basically there are two layers of charged particles. पहला ये वाला होगा fixed layer, the other one is the diffused layer, and this double layer is called Helmholtz electrical double layer. And how are these surrounding is because of adsorption again. Van der Waals forces come into picture. One is neutral, one is charged, so it could be a dipole induced dipole thing also. So multiple factors. It depends on kiska colloid le rahe and what's going on in that solution. ठीक है.
Yes, ma'am, got it.
Okay. Simple. Like if I had to summarize the story, charged, like colloids always are charged Like they are charged particles. It's the charge that's giving them the stability because like charges repel. Now, when they are in a solution, opposite charges attract. So you have colloidal charged particle. It attracts the opposite charged particle that ends up forming a double layer of electric charges. So it's an electrical double layer. That's all it is. Now, which charge like under positive hoga ki negative hoga, all of that varies from colloid to colloid. तो अगर वो पॉजिटिव कोलॉइड है तो यहाँ पे सारे पॉजिटिव चार्जेस रहेंगे, इट अट्रैक्ट्स द नेगेटिव चार्ज. एंड इफ इट्स अ नेगेटिव कोलॉइड, यहाँ पे सारे नेगेटिव चार्ज रहेंगे, इट अट्रैक्ट्स द पॉजिटिव चार्ज. सो दैट वेरीज फ्रॉम कोलॉइड टू कोलॉइड. Where is this charge coming from? That also again varies from colloid to colloid. Selective adsorption is the most popular theory, but it can also be formed like soap ke case mein. The colloids are already ionic particles, so they all like associated micelles, like they clump together to form these associated micelles that ends up being charged on the outside. Sometimes it could be an electrical capture depending on the method of preparation. So it can be due to many different reasons depending on the color. Okay?
Yes, ma'am, got it.
Okay. So one last thing related to charge. Now, whenever you have a difference in charge, यहाँ पे एक positive charge है, second like अंदर एक negative charge है. What does that end up in? So instead of difference, let me say whenever you have a charge separation. So there's separation of charges between the fixed and diffused layers. Like it gives rise to what? Like when, like not just in colloids, in any context, if you hear charge separation of charges, like one is at a positive charge, the other is at a negative charge. What happens between both of these?
Electrolysis sort of a thing, or
Electrolysis?
dissociation due to.
No. That's a proper process. Think of neuron mein, you have charge separation. Like यहाँ पे one side is at a higher charge, like a lot of charge is accumulated on one end and there is less charge on the other end. So what happens between both these ends?
The charge is relayed
Because
of the difference in the magnitude of charges, or
let me put it this way. All of you all have handled batteries, right? Dry cell.
yes, ma'am.
So how would you describe a dry cell? Cylinder hai.
A dry cell, yeah, it's a cylinder which consists of chemicals in it, okay,
Yes.
which dissociate and move from, I think, the positive end to the negative end.
So you
There's
have
a charge difference which is created
Yes.
within the battery due
So-
to electrons.
Yes. So what is this charge difference creating?
It is allowing the electrons to flow from one point to
Yeah. What is
another.
that called? What is that thing that moves the
Current.
electrons? Motion of electrons is current, but what is that factor that moves the electrons? The force that moves the electrons. You all have
Electric
like
potential.
potential, correct.
Yes, sorry, it took me like a little bit time to get there.
Like you all like have left those concepts back in term 1 now.
Big time, man, big time.
So this again, there's separation of charges between fixed and diffused layer. So this separation of charges, it gives rise to electric potential. Same concept as everywhere else, but in this case, the names are different depending on where you're applying it. So in this case, it is called electrokinetic potential. Or simpler name, zeta potential. Zeta is again a Greek alphabet like alpha, beta, gamma. So zeta potential. Okay. Remember, we're just talking about properties of colloids, right? Properties matlab we're just discussing ki, oh, colloids mein aisa hota hai. Oh, this is how they behave. Oh, this is what we can find in it. So colloids have charges. That is one more property. That's what they do. Like they end up being charged. And because of this charge, they attract opposite charge, which creates two layers, a double layer. And this charge separation ki wajah se, they end up having something called a zeta potential. So we'll revisit zeta potential when we talk about coagulation and other aspects. Okay, Dhriti, Ansh, Shantanu, is this clear, you guys? Like, you've been really quiet so far.
Yes, ma'am. It's clear.
Pakka? Okay, Dhriti, Ansh, you guys there?
Yes, ma'am.
Okay, clear?
Yes.
Okay. So if you're clear about this, if you have like a basic understanding of what's happening, just give it a read, revise it later on. It'll become like, it'll be cemented in your head, basically. Yeah. Dhriti, are you there? Hello, Dhriti? In case you're speaking, you are still under mute.
Ma'am, just to confirm, that is zeta potential, right?
Yeah, ZETA, zeta.
Yeah, okay.
Zeta ka symbol kind of looks like this, I think. I have to Google it. I don't remember it. But yeah, it's a Greek alphabet basically. Okay. Can any of you just like ping Dhriti, see if everything's okay if she's here? So about zeta potential, so if you add extra electrolyte, so addition of more electrolyte, more electrolyte. Like for example, AGI here, so potassium iodide, we are preparing AGI. So if I add more Ki solution, so if I add more electrolyte, the zeta potential is reduced. So why, how does it affect? So the reason is that, so adding more electrolyte, you're adding more charges into the solution. So that leads to reduction in the repulsions. So if there is a reduction in the repulsion, that causes coagulation. Repulsion kam hua matlab there's attractive forces, so all of them end up coagulating, and coagulation and or precipitation matlab it's no longer a colloid. So you've basically like destroyed the stability of the colloid. Okay. So addition of, like, we'll revisit this, addition of electrolyte is one way you can separate the components out, because doing so, it reduces the repulsion between the individual colloidal particles, and that results in coagulation or precipitation of this inside precipitate. Okay. So then we have electrophoresis and coagulation, which is kind of related to whatever we did. So that's gonna happen quickly. So go to the next point, next property. Also, have you guys heard from Dhriti? What's going on?
No, ma'am. I'll just check him.
I'll ping on the, okay. Otherwise, I'll ping on the group is here.
Ma'am, is this electrophoresis method same as the one that we do in biology?
Gel electrophoresis you're talking about?
Yes, ma'am.
Yes. So here we'll
It's
just
exactly
discuss
the same.
the principle of it. What you do in biology
Okay.
builds up on this.
Mhm.
So what do you do in biology? Let's start with that.
So, ma'am, gel electrophoresis, the second, it's so to give you a gist of it, first you take out, like you separate out the DNA. Okay, now DNA is 2 meters long, correct? So you cut it using enzymes. Then the final, when you cut it, it's all mixed, right? There are like different lengths of DNA present. So you use gel electrophoresis to separate the different lengths of DNA. So when you do gel electrophoresis, you sort of like load separate DNAs into these compartment sort of things, and then you apply. Now DNA is a negatively charged molecule, correct? So then you apply like an electric potential from negative to positive. So across the entire matrix or the grid sort of a thing, which is made up of like it has like it's basically made of like
It's like a sieve.
gel, which
Like you
is,
have
yes,
holes.
exactly. And yeah, it's like a gel seaweed matrix sort of a thing. So when you apply the electric potential, the longer lengths of DNA, they're much closer to the compartments, as in they move at a much slower pace than the ones that move, like the ones that are like smaller in size, they move at a much quicker pace and they reach like the end of the matrix very quickly. So
Yeah,
that's
and
how you separate out the different lengths of DNA.
yes. So that's an application of electrophoresis. Now
Hmm.
we'll discuss the principle behind it. कि क्या हो रहा है. Okay. So electrophoresis is, so from what Mitali has said, basically DNA is negatively charged and it moves towards the positive end is what she's saying. So that movement is called electrophoresis, and this is applicable to all the colloids. Okay, so this is also called cataphoresis, CATA, cataphoresis. another name to it, just a different word. So this is an activity or an experiment or whatever you call it, to prove that colloids have charged particles. All the colloids are charged particles. So to prove that colloids are charged, and you can use this particular activity like by measuring the speed of the movement and all to measure the zeta potential. Ki kitna charge hai, how strong is that charge separation there. So zeta kind of looks like this. Or you can just write zeta potential. Okay. So what happens here is, so Mitali, you said you take like a sieved, like a gel thing, all of that, right? So that is
Yeah,
specific
ma'am.
because you're using it to separate out DNA segments. But
Mhm.
in general, like in order to, if you want to apply it to any random colloid, like the AGI colloid, the solid
Correct.
that we saw, that sort of a thing, you just use a U tube, not the video kind, a literal
Mhm.
U-shaped tube. So yahan se, like you can separate out the thing. There's like a stopper, which basically keeps the liquid in. Upper, you fit it with electrodes. So you have differently charged electrodes on each side. This is connected to a circuit. Like, of course, you have rest of it set up there. Now, the whole thing, like the electrodes are submerged in the colloid sol, the colloid, whatever we're taking. Abhi colloid mein you have suspended particles, right? The suspended, like dispersed particles are the ones that are charged, and then dispersion medium may you would have like the opposite charges and all that. So on application, like once you complete the circuit, switch on the switch, the electrodes are going to get charges. Let's say this is positively charged and negatively charged. So if it is a negatively charged sol, it will be attracted to the positive electrode, and if it's a positively charged sol or colloid, it will be attracted to the negative electrode. So by the end of the experiment, you would have like the colloidal particles, all of them coagulated or, like accumulated on one of the two sides, depending on which charge they have. So this, like initially they were suspended, displaced throughout. On addition, like once you start this experiment, once you apply this electricity, all of these particles are going to move towards the opposite uh, charge, oppositely charged electrode. So this movement is what is called electrophoresis. Okay. So main points are,
One thing is that how is it any different from electrolysis?
electrolysis may you have ions moving towards the electrodes, and you like electrolysis in the name itself, it's there, right? So electro meaning you're using electricity to lyse something, to break down something. So you may be breaking down water like H2O. If you do electrolysis, you end up separating it into H2 plus O2, which you get at different electrodes. एक cathode
Yes,
पे,
ma'am.
cathode पे. So electrolysis is a literal chemical reaction that is happening due to the application of electricity. Electrophoresis is simply like इसमें chemical change नहीं हो रहा है. The colloidal particles are separating out. That's all that is happening. The composition is not like you're not getting completely new chemicals out of this. So this is just separation of the colloid. Okay. So just to summarize this again, you have a U-shaped tube with electrodes, like they're fitted with electrodes on the ends of the U. So on application of electricity, the colloidal particles move towards the opposite one. यहाँ पे मैंने positive के पास दिखाया, but depending on what charge the colloid itself has, it's going to move towards the opposite charge. So on application of electricity, so colloidal particles move towards the opposite electrode. Opposite electrode in the sense, okay, I'll write oppositely charged electrode. Okay, so this movement is called electrophoresis. Okay, so one is like a lot of times whenever you need to separate out components of a colloid, you can use electrophoresis. So gel electrophoresis is an example of that application. So DNA is so you have a colloidal solution of DNA in the gel. So you have like electric sieve and all that. So on application of electrolysis, the DNA segments move towards the opposite charge, so negative to positive. Then you add additional stuff like the whole sieve that you add, and how you prepare that fragments of DNA, like based on the size and all, that is to fulfill your reason for this doing this thing, which is to separate out fragments of DNA. But the reason it moves is like electrophoresis. It's a colloid, opposite charge, and it moves there. That's the thing. So another application is like if you had to measure the zeta potential, then using speed of the movement, you can measure the zeta potential. So we're not going so deep into that, but basically you have all the variables, like you know how much potential you've applied and you see how fast the particles are going. Then based on that, you can figure out how much is the attractive force, and like that in turn, you can apply the formula to get your zeta potential. Another case in this, so for any reason, the colloid particles are not moving, but the dispersion medium is moving. Suppose somehow you manipulate it, or maybe because of a property of the colloid, the dispersed phase doesn't move. Instead, if the dispersion medium is moving, in that case, it is called electro osmosis. So usually it's the colloid particles, the dispersed phase, that moves in electrophoresis. But if the opposite happens where the medium is the one that's moving, then that's called electro osmosis. Just like your osmosis. Osmosis, the solvent is the one that's like going from like higher concentration to lower concentration, right? So similarly, in this, lower concentration to higher. Solvent is moving from lower to higher. So in this case, because it's happening due to application of electrolysis, this will be called electro osmosis. So DM is moving instead of the colloid particles, like the particles that make up the colloid. Okay, so that is it for electrophoresis. And finally, we talk about coagulation. This is also very, very theoretical. Like, how do you coagulate salts? Coagulate matlab you basically clump together all the dispersed phase so that you can separate it out. Okay, Mitali is done. Dhriti, Ansh, Shantanu, what about you guys?
Yes, ma'am.
Yes, ma'am.
Okay, but so far all clear, like makes sense. Like, is it making logical sense or is it completely like sounding like something? Yeah, okay, take your word for it. So next, talking about coagulation. The colloid, the whole deal about colloid.
Class is till what time?
Initially I thought we can end it at 5, but this is like the last one that is left because emulsions anyways
Yes,
delete.
ma'am, we can finish that and then we
Okay,
can.
ma'am.
So it's the only thing that's left. 5 methods hai, Fadafat. So half of it we've already done while discussing the previous thing. So I'll quickly go over it. So coagulation, you guys already know, basically like clumping together of things. That's coagulation. This is also called precipitation because it's all dispersed and then you're bringing it all together. So you're precipitating out these particles. Also called flocculation. So all of these refer to the same process, same phenomena, just different words used for it, maybe in different contexts. But yeah. So basically, stability of colloids is due to the charge that is present on them. So if you remove the charge, it becomes easy to coagulate them. So coagulate. So just remove the charge, the stability is gone. So especially in the case of lyophobic salts where there is repulsion, like the thing doesn't mix very easily, it won't mix. They'll just come out of the solution just like that. So all the methods that we discuss are all relating to how do we get rid of this charge here. So first method is using electrophoresis. So this is pretty self-explanatory. We just discussed electrophoresis. You're literally attracting all of the particles with the same charge to one end. So once all of them have clumped together, just like it's easy to remove them from here. Skim them out, use a different setup, do whatever. But basically, you've achieved this separation. Coagulation ho gaya. Next method is, oh yeah, to mix oppositely charged salts together. So this is called mutual coagulation. It's like a 2-in-1. So if you want to precipitate out two different salts, they happen to have opposite charge. Mix them, they'll do the work against each other, and then you'll have all of them precipitated out. So what happens is you have a positive sol and a negative sol. You're adding oppositely charged particles to this thing. So the negative sol has negative particles predominantly, like all the colloidal particles have negative charge. So that's going to attract the positive charge. So if you're getting rid of the repulsion, more attraction means clumping together, like they'll all be attracted.
The molecules will be together. Yeah. So they'll reach some sort of like a neutral level.
Yes. So they'll be neutralized. That's the key word. Good. So this is also called mutual coagulation because they're both the opposite charges are coagulating each other. Then we have boiling. This is more of a physical thing, way to remove the charge. The whole deal about colloids is that like they are all suspended and then you have Brownian motion going on. The charges are adsorbed on the surface of the precipitate particles. When you boil them, the motion of these particles increases. You're giving them more energy. So by giving them more energy, the motion increases, Adsorption also, if you remember, physical adsorption may, it happens at lower temperatures. Higher temperatures may, the attractive forces are just not sufficient to keep them together. So that way, by increasing the temperature, when you boil the mixture, you're increasing the temperature, you're getting rid of the attractive forces on these charged particles. So all of them will come out. For persistent dialysis. Now, you remember what dialysis is?
Yes, ma'am.
Okay. So dialysis is a way of purifying colloids. So you're removing some like particles that are not related, especially in electrodialysis, using electricity or removing like certain charged particles. Persistent dialysis. So if you do dialysis for a prolonged period of time. Oh, Diti, okay. So were you following throughout? Like, have things been clear?
Yeah, ma'am, just a little. I had to miss because in the middle because I had gone to take my injection.
Ah, okay.
But that's okay. I'll go through the textbook, and if I have doubts, I'll let you know.
Yeah,
It's
and
not
this
very-
recording will be updated, so you can just refer to that.
Yeah.
Yeah. Cool. So if in case you had to leave for any reason, just like give me a warning so that I know, and then let
Yeah,
me
I forgot. I mean, I do it all the time. I just forgot it this time. I'm really sorry.
Cool. All right. Now we're talking about persistent dialysis. Dialysis may so like let's say this is the tube. Sorry. This is the semi-permeable membrane. Some particles are caught, others are gone. Remember when we were talking about lyophilic, lyophobic salts, lyophobic may you needed to have a stabilizer. So in a lot of cases, like the AGI, KI solution, this sort of a case, think of the I minus surrounding the AGI as the stabilizer, because this is the one providing the charge that contributes towards the stability of this thing. So by doing persistent dialysis, if you end up removing the electrolyte, so you're purifying the colloid excessively to so much of an extent that you're removing the agent that causes the stability. So if the electrolyte is removed, then there is no charge on the particles, the colloidal particles ends up being unstable, and coagulation ends up in coagulation, like the precipitate comes out of the mixture. Okay, so in persistent dialysis, what is causing the precipitation, the coagulation, is the removal of the electrolyte, basically, removal of the charged particles. And finally, last method is by adding more electrolytes. So addition of electrolytes, remember we discussed this when we were doing this. So addition of more electrolytes decreases the zeta potential. So because there is reduction in the repulsion, you're adding a lot of ionic particles that ends up with coagulation or precipitation. Yeah, so these are like the 5 methods of coagulation, just going over it again. Electrophoresis may, you're separating the charged particles out, the dispersed particles out, literally by attracting them using electricity. Mixing oppositely charged salts, that is mutual coagulation. Positive, negative, both are charged particles coming together. Neutralization happens, and then if there is no charge, there is no colloid. Boiling, you're increasing the temperature so much that whatever charge is adsorbed over the colloid particles, they get separated out. Again, no charge, no stability leads to coagulation. Persistent dialysis, you're removing the electrolyte by continuing dialysis for so long that the electrolyte is removed. Again, electrolyte removed matlab no charge, coagulation. Adding electrolytes is doing the same thing, like the other extreme of it. Adding more electrolytes reduces zeta potential, results in coagulation. Okay. So these are the 5 methods. There's a little bit of extra text related to the 5th point, which is by adding electrolytes. So there's something called coagulating. So basically, when you add electrolytes, you're adding more charged particles. So the oppositely charged particle is going to neutralize the one present on the colloid. So that species of ion that is actually causing the coagulation, that's called coagulating ion.
So, ma'am, can you take an example here? For example, if you take the electrolyte or example that we took, we have Ki in the thing, and then we add AgNO3. So,
No,
what
this is
would
the
be
colloid
the
that is already existing. So
yeah?
HCI here adsorbs I minus, forms the colloid,
Hmm.
and you have a double layer and all that. If I add
Hmm.
more electrolyte, if I add, let's say, NaCl solution or anything else, the excessive ions like the Na plus is going to attract the I minus ions, get it out of here. Like basically, it's going to neutralize whatever charges are there around it. So unke forces will be a lot more dominating compared to whatever adsorbing forces this particular particle will have.
Okay, ma'am.
Yeah. So the oppositely charged ion will end up neutralizing it. So they interact, neutralize. So the charge is gone, coagulation happens. So it's called coagulating ion or flocculating ion, the one that's doing the neutralizing. Then related to this, you have something called the Hardy-Schulz rule. So basically, Hardy and Schulz, team of 2 scientists, so they have done some work, experiments about coagulation of colloids, and they realized that the valency of the valency of this particular ion, coagulating ion or flocculating ion, is directly proportional to the power of precipitation. Okay. So if I add electrolytes containing a higher valency, something like electrolytes with Fe3 plus or Al3 plus or Mg2 plus, they will coagulate or separate out the colloid much faster and more effectively than an electrolyte with NaCl or KCl, like lower valency. Okay. So higher is the valency of this coagulating ion, higher is the power of the precipitation. Similarly, there's other calculations also related to it. You have something called coagulating value. So it's very technical. It's the minimum concentration of the electrolyte required to cause the precipitation in 2 hours. In 2 hours, and it is measured in milliliters per liter. So you have coagulating value. So using these, you can it'll help you choose what electrolyte to use to coagulate a particular colloidal solution. So just measurements related to it. So this is the minimum concentration of the electrolyte. So required to cause precipitation in 2 hours.
Got
what
it,
are
ma'am.
Huh. So this is all for lyophobic salts. For lyophilic salts, again, the stability is due to the charge that is always there and solvation. Lyophilic ke liye, adding electrolytes works, and adding a suitable solvent also works because you're disturbing the solvation of it. Do you guys remember what is solvation? So in this case, the stability is due to one charge and two solvation. Do you remember what is solvation? So in
Ma'am,
order,
isn't solvation where the dispersion medium and the dispersion phase mix easily?
not exactly. Do you guys remember like thermodynamics when we were doing hydration, enthalpy of hydration, enthalpy of solvation?
Yeah, we had solvation enthalpy.
Hmm. So uska
So like the energy released
हाँ,
or something like that.
yeah,
Okay.
yeah.
When
Enthalpy
two
of,
solutions are mixed.
correct. So enthalpy of solvation is the energy released on dissolving something, on mixing two components to create that solution. Uska equivalent is hydration. So when you put any like NaCl or something in water, like when they dissociate into ions, these ions are surrounded by water molecules, right? That's what causes them to be stable enough to remain as ions. So this phenomenon where these water molecules are surrounding it, so that's called hydration. And remember, we were talking about smaller the ion, higher the hydration, it affects the mobility of the ion and all of that. That in turn affects the reducing nature. If you don't recall, it's fine. But basically, when you add ions in water, the water molecules surround it. So solvation is similar. So it is the phenomenon where the solvent molecules are basically surrounding a particular this thing, a particular solute. So lyophilic salts may, because both of them are mixing each other. So apart from charge, there is solvation also involved between dispersed phase and dispersed medium. So disturb either of these two things and then you can cause coagulation. So in order to disturb the charge, neutralize the charge, so you add electrolyte. In order to disturb the solvation of it, you add a suitable solvent. So for example, in this case, suppose we have a hydrophilic salt. So basically a salt in which the dispersion medium is water, so water based thing. So if you add a little bit of alcohol or acetone, so this leads to dehydration uh, of the colloidal particle. So basically the water molecules that are surrounding the colloid particle, they will be pulled away because of the addition of the alcohol or acetone. So that dehydration is taking place. So solvation come ho gaya. So stability is reduced, matlab that's gonna lead to coagulation. Yeah, make sense?
Yes, ma'am, it does.
Okay.
Yeah,
And
ma'am.
that's it. Cool. So there's a little bit about protection of colloids. Suppose you have lyophobic colloids, they are unstable, so they need some protection. So lyophilic protects lyophobic. So that helps with addition of like stability. So they are also, that's why they're called protective salts also. So lyophilic protects lyophobic salts. This is one thing. So kind of forms, so if you add a lyophilic salt to a lyophobic salt, it kind of forms a protective layer around these lyophobic colloidal particles. And once they're surrounded by lyophilic, these are good with that stability. So yeah. And that is the end of the chapter.
Ma'am, could you go back to the previous slide?
Here you go.
Yes, ma'am, done. So that means we're done with surface chemistry, right?
Yes.